Thank you very much for the introduction. Do you see my presentation?
Yes, we do.
Okay,
Please.
very good.
Yeah.
So first, let me introduce myself a bit before moving to the main topic. I am a statistical physicist working on collective phenomena, mostly on fish schools and human groups. And let me also mention that for the past 10 years, I have benefited from a very fruitful collaboration with Guy Terolaz and his group, also in Toulouse. And finally, let me mention that I participate in the design, in the realization, and obviously on the analysis and modeling of experiments. Here, I'm showing you some of the groups I'm collaborating with on humans, including Dr. Kameda that we just heard before. So let me present you the experimental setup. We have individuals walking in circles which are drawn on the ground, and they have sensors on their shoulder which allows us to track them. You probably see them on the video. And let me already mention that these sensors, which allows us to track them, have also the possibility to emit a beep, which is controlled by the system, by the computer. And we'll talk about this beep later. But the first goal of our experiment was actually to design a faithful model of walking pedestrians using a methodology that I will not have time to describe here, but which we have also applied on fish schools. And essentially, the idea is to record a lot of trajectories of one individual walking, you see inside the blue circle here, for instance, and of course, many repetitions to, for instance, infer, in this case, the interaction between the subject and the boundary of the arena. And we repeat the same kind of experiment with many groups of two individuals, two humans or two fish for fish schools, to also measure the social interaction and for humans, the repulsion between two individuals. So from there, we can, it's a very long story actually, but here only in one slide, we can actually implement this measured interaction to in a model, in a mathematical model, and then test this model. Here I'm just showing you a few observables that we have measured in groups of 22 subjects. So the model is in red, the experiment is in black, and for instance, we measure the distribution, the probability distribution of the speed of individuals, of the distance between closest, nearest neighbors, the distance from the center, and even quite subtle quantities like correlation functions, for instance, the speed correlation function or the mean square displacement, which really allows to probe a very subtle aspect of the dynamics. So we have a model for walking pedestrians. So now let's go to the fun experiments where we consider groups of 22 individuals. Each subject was randomly assigned a color, blue and red. And what is very important to remember is that each subject actually do not know their own color, and they don't know the color of the other subjects. Only the system, the computer, knows that. And I will show you movies of the experiment. Let me just mention the instruction that we gave to the subject. So after a period of random walking, the sensors of the subject would be turned on, and they would begin to beep when the environment of a subject is not of the same color as him or her. So let's see movies from the experiment. I will show you two runs. So here we are in the random walking phase. And as we turn on the beeps, you see that some of the subject have their color surrounded by a white line. So it means that the beep is on, and again the sensor is beeping when the subject is surrounded by a subject from the other color. Here, for instance, you see this red guy here, and which obviously made some blue guys beeping when it approached them. So ultimately, the experiment stops where nobody beeps anymore. So the first question was, would it happen? And yes, in all our runs, ultimately, the subject reached a configuration where nobody is beeping anymore. So sometimes, as you can see on the right, the final configuration was well separated, whereas on the left you see several groups of blue and red. So obviously I didn't tell you what was the environment, what was the actual condition for the sensor to beep. And we actually didn't tell our subject, and we were very surprised that they never asked what was the environment. In fact, in practice, the environment was characterized by an odd number that we will call K, which goes between 1 and 13. And a subject was beeping if the majority of his K nearest neighbor was not of the same color as him or her. So let me give you an example for K equal 1. So here you have the focal individual, and the nearest neighbor is also red. So this guy here is not beeping. But for instance, for K equal 3, the 3 nearest neighbor are shown here. And you see that 2 of them are blue and 1 of them is red. So the majority of the K nearest neighbor is of opposite color. So this person here would have its beep on. And obviously, this is generalized to any value of K, of odd K. So let me show you some, let me first mention that obviously in the experiment, we had the full control of the value of K, which was, and we repeated typically 25 experiments per value of K in a random protocol. Another aspect which is very interesting, but unfortunately I won't have time to really develop it here, is the fact that this beep constitutes an artificial sensory device, a bit like the human eye, in the sense that this device is limited by its range of perception, K, the range of the beep, but it also filters the information because the actual information is the position and the color of the K nearest neighbor, but ultimately the information is filtered by a simple beep on or off. And we see it's very big filtering, but even the human eye, for instance, you only perceive certain wavelengths. So you have also a filtering of information. So we have really a true artificial sensory device. So let me show you a picture of a typical final states of the experiment when nobody beeps anymore. And what I will show you first intuitively is that for small K, you can see that quite often you have several groups. Sometimes you have also only 2 groups. We had a clean way to define the groups. I will not enter into details here, but there is a very clean way to do it. And as the K is increasing, as you will see, you get more and more perfect separation between the groups, especially when K is bigger than 7. So let me actually quantify this thing by measuring the probability of having a group of a given size for different value of k. And as you can see, as k is increasing, the probability to have groups less than 11 is decreasing until becoming very small. On the last graph here, I'm showing the full distribution, but at a different scale, just to show you the peak at group size 11. That means a perfect group of the same color. And as you can see, it increased with the value of k and ultimately saturates. So the red curves here are the model. And let me mention that in the model, we exploited, obviously, our walking pedestrian model. And we added to that a very simple strategy, meaning that in the model, when an agent was beeping, it would move, whereas if it was not beeping, it would simply stop and maybe resume walking if it's beeping again. So let me also show you a quantification of the dynamics. In violet, I show you the fraction of people who are still beeping, and it's ultimately going to zero, essentially in an exponential way. And in black, I'm showing you the number of groups, which ultimately saturates to certain value, which depends on k, as we have seen. And again, I show you the simulation of the model in red. So let's have a movie, and maybe let's do a kind of Turing test. So here I show you a movie of an experiment and of simulation of the model. And again, when you see a circle surrounded by a white line, it means that the individual is beeping. So this experiment and simulation are for k equals 3. That is, an individual is beeping when the majority of his 3 nearest neighbor is of the opposite color. And you see that in both cases, we took a run for which the simulation and the model was leading to 4 groups. And I don't know if you guessed, but the experiment was on the left. Let me just finish by mentioning that you can also quantify the average group size, which, as I have mentioned before, is ultimately saturating around k equals 7, showing that there is an optimal minimal information that you need to accomplish the task of separating in the best way. Let me also mention an interesting experiment that we did, which is shown here in blue, where the experiment was exactly the same, except that we asked the subject at the end of the experiment, there should be 2 clearly visible groups. So you could have imagined that people could have applied this strategy without us telling them to do it. Again, we asked them that at the end of the experiment, there was 2 clearly visible groups. And you see that in that case, the average group size is almost 11, that is perfect segregation. And actually, the fraction of experiment with perfect segregation, again, is almost going to 100%. So let me conclude. Again, we have another example of a very rich collective behavior which emerged from social interactions. And let me really add that within my collaboration with, especially with Guy, our focus is really to try to measure social interaction, local interaction in humans and fish, and to try to understand how they lead to the emergence of complex behavior. And in this experiment, that's exactly what we did. First, measure this social interaction, implement them in a model of pedestrian walk, and then ask the human subject and our model to do a more complicated task, which is this phase separation dynamics. So we implemented a very simple sensory device, which is controlled just by its range, K, and which allows our subject to solve the problem, even if they were not actually aware of the nature of the environment, which was essentially set by the majority of the K nearest neighbor. And we found a kind of optimal range, K equals 7. We actually also made simulation for larger size of larger number of subjects for the model. Let me also mention that this experiment allowed us to control the separation and the polarization, in a sense, of our group. So obviously, this is a very important issue in many social contexts. More and more on the social network, we have a kind of phase separation and segregation, even polarization phenomena. And let me actually mention that we actually showed that our experiment had a very clear and one-to-one correspondence with an actual physical phase separation. So I'm done. Let me thank you for your attention, and also thanks my collaborator, Guy Terolaz and his group, and also the people at LAS who designed the tracking interface. And I also give you the reference of the paper here.